Hello all, in this tutorial we are trying to attempt the same image processing, the image filtering operation using hardware, which we did using software in the previous tutorial. So remember, we already built our custom IP core for image filtering few tutorials back. So this one, and there was a slight mistake which I have corrected here. So I have updated my block design using this updated IP. In addition to that, I'm making few more modification. One is on this Axi DMA controller, which we instantiated before. So I have changed few parameters. One parameter is this buffer length register. I guess before it was 12-bit. This is basically saying the size of the register where the processor is going to configure the size of the DMA transfer. So if it is only 12-bit or 13-bit, you can transfer only 2 to the power of that many bits. Okay, so if it is 12 bits, I can transfer only 4 kilobytes using DMA in one shot. So our image size is around 250 KB, so we will have to transfer multiple times. So we don't want that. For better performance, we want to transfer all data in one shot. So the maximum size supported is 23 bits. That means you can transfer 2 to the power of 23 minus 1 bits, which is approximately 8 megabytes. So that is one change I have done. Another change I have done is I have changed the maximum burst size. This is for the Axi interface. So the larger the burst size, the better will be the read and write performance from the memory. So I have increased it to the maximum value 256. Another thing that I have done is I have enabled this option allow unaligned transfer. So what it does is, if you are saying Axi stream width as 32-bit, there is a requirement that the memory from which you read or write should be a multiple of 4, because this is 4 bytes, 32 bits. So the memory from which you start reading or writing should be a multiple of 4, 0, 4, 8, 12, etc. Now in my software, I am doing memory allocation at a byte level, so it doesn't guarantee that the malloc function is going to return me an address which is a multiple of 4, because I am doing malloc using U8. So he can return me a buffer whose starting address is 0, 1, 2, 3, any number at byte addressing. So that may cause issue. So if I check this option, allow unaligned transfer, the starting address doesn't matter. It might not be a multiple of 4. Okay, so this alignment problem, the data transferring starting address a multiple of 4, you may see in many other places also, especially when we go for PCI Express design and all. There also this requirement is the starting address should be a multiple of 4. These are due to some internal architecture details of the processor and the system, so it doesn't matter. So remember to make these changes, change the width of buffer length register, and enable unaligned transfer and increase the burst size. So how it is going to affect your design, these parameters, they are actually passed to the source code, and finally what is going to happen is the resource utilization of your DMA controller is likely going to increase because of this change in parameters. Okay, so that's only the side effect. Okay, after these changes, otherwise the design is exactly the same that we done a couple of videos back for testing the DMA controller, and generate bit stream. So I have generated till bit stream. After that, I'm going to export it, hardware, and launching software. So I have made a fresh copy. I just copy pasted the folder where I have kept this project before, so that I don't destroy my previous project, because it was working fine. So I don't want to destroy that project. So that's why I made a fresh project. So you can also do the same thing, and you may delete the .stk folder inside that folder and start the SDK product fresh. That's what I'm doing. So here I'm starting a new project, application project. Let me call it hardware image filtering, next, and an empty application. So we already have the source code for the DMA controller initialization, things like that. So you can either start a C code source file and copy paste from your old source code, or I can do the proper way of doing it. So what you should do is you should go choose import, and you go to general, choose file system, and you browse to the folder from where you want to copy the source code. So in my case, it is in this computer. Vivado folder, DMA system. This is my old folder. I am currently working here. I made a copy of that folder. I am currently working on here. So I go to my old folder and DMA test source. Okay, so this is my old source file. So he's asking which old files you want to choose. I'm choosing only DMA test because I want to copy only that file. I don't want to copy any other file, and you just say finish. So what happens is a copy of that file comes into your current project. Okay, so this is the proper way of importing source code, either written by you or something that you got from others using the import method. Okay, so what I want to do is, to this code, I want to integrate the code which I use for transmitting image to my system and sending it back. So that part I want to integrate. So you can also import it over here. Better, I'm going to copy it. So I'm going to my other project, data transfer, image inversion, source, image inversion. Okay, so this is my old code. So I'm copying all of them to my current project. And okay, so this entire code for initializing DMA I am copying, and I am keeping it at the beginning. I'll delete this array. This was used for just testing the simple DMA transfer, so let me delete it. This part I will keep. This part was the initialization for the DMA controller, so I'm keeping it as such. Now remember, in the linker script last time you increase the size because you are using a large buffer for storing your image. So let me increase heap size. Last time we used 100,000, but what I observed is even with 100,000 sometimes it is failing. So I'm just putting 200,000 this time, and I'm slightly modifying my code here because even with 100,000, 200,000, sometimes this malloc function may fail. So we need to check whether the function was really successful or not. So how can we do it? So this function is actually returning a pointer actually. So this is a pointer which points to the starting address of the allocated memory block. Okay, so this value will be either 0 or a negative number depending upon the system if the malloc function fails. So we can actually check if image data, if it is less than or equal to 0, that means I can just print memory allocation failed. So once memory allocation failed, there is no point in going further. I can stop my program and exit. Okay, so we will proceed only if the memory allocation is successful. So ideally in the previous code also you should add this to check whether memory allocation is successful or not. Okay, otherwise it's fine. So we initialize the DMA transfer. So okay, so this is where we send data to the DMA. So before that, what we'll do is we'll add the code for transferring data from computer to the DDR, which we already have from our previous project. So I'm copying it and I'm putting it here. So data transfer from computer to DDR through the UART interface. So the code remains the same. Now this status before data transfer, this we added last time just for debugging purpose to check whether DMA controller is in halted state or not. You can either keep it or you can delete it. Now this we did the cache flush to make sure the cache is not causing trouble. That means the data coming from the processor maybe in the cache, it is not in the DDR. So if you try to transfer data from DDR to the IP through the DMA, you will be getting the old data instead of the new data. So it seems like this time we are sending data to the DDR through the UART interface. Okay, so this is the function used for that. So it appears that the processor is not playing any role here, but that is not the case. So what is happening inside this function is the processor is reading from one of the registers of the UART controller in the PS, and the processor writes it to the memory. So this is still some kind of PIO operation inside the PS. The processor reads from the UART controller, then he writes it to the DDR. So although you cannot directly see the in function here, that is happening in the background. Okay, so we still need to flush the cache. So either you can use this function CILD cache flush range, where you have to give the starting address from where you want to flush and how much data you want to flush. So in this case, the starting address will be this one, image data, and how much you want to flush. You want to flush this much file size, that many bytes. Okay, so you can either write like this, or you can use the function CILD cache flush, which will flush the entire cache. Okay, so it may take a little bit more time, but does the job. So either of them are fine. And this was the function for DMA transfer. So remember, we are initializing the reception first, then we are configuring the transmission. Okay, so reception should be initialized first. So this part remains same, pointed to the DMA controller. This one is the buffer where the received data should be saved. So in our case, we have some buffer in the DDR after malloc, this one. So the initial image is sitting here, as well as the process image should come back to the same buffer. Or you can allocate another memory to do it, but same memory will do. So what I will do is I will copy this one from here, and I will put here. This is the starting address. Now don't put ampersand here, because he's expecting an address here, a pointer, and image data itself is a pointer, itself is an address. So you should put it here. Here we are using ampersand because I am not directly using image data. I am using the array style of representation, image data of total received bytes. Okay, so this should be taken together, and he is expecting an address. So in that case, you need to put ampersand if you are using this array style. Okay, so if you are using just image data, no need to put ampersand. But if you are using image data of 0 like this, you need to put ampersand here to represent this is an address. Okay. Now, how much data we want to transfer? We want to transfer how much data? Oh, I guess I made a mistake. So if you write like this, he will transfer from the beginning onwards, which includes the header part also, right? So we need to change it. I need to transfer only from the header. So now I need to put the ampersand. Otherwise, he will be filtering the header also. Okay, so we don't want that to happen. So this is the correct one. How much data you want to transfer? You want to transfer the image part, only the image part. So we configure it, image size. This is the reception part. Same way, transmission, everything will look exactly same. You want to transmit starting from this address. You want to transmit this much data, and this is the direction. So this is the only difference. First one is saying you need to transfer from device to memory. Second one, you are transferring from memory to the device. Now this status checking you can do after this one also to make sure both are fine. Then status equal to halted, status. Okay, so everything should be fine. So this print was again for testing. I can remove it, and I can put the code for transferring data back from memory to the computer. So I can copy paste this part. Okay, so remember this is the part where filtering is happening in the software, so we don't want that part, and this is the part where it is sending back. So instead of this we have the DMA part. Okay, so we paste it back, and okay, so this one is actually this one. Okay, DMA data to the IP core and process. That is what is doing this. Send it back. This 2 microsecond, again let me first try with 1 microsecond delay to check whether things will be faster. You save it, yeah, no errors, no one, everything looks fine. So you can go to run configuration, and let's configure standalone application, apply, close. Okay, so now you should connect your board, and this time also I'm going to program from Vivado. So open target, auto connect. Program. We still have our debug core, but if you wish you can see how signals are changing. Okay, now take the rotom, configure everything, enable log. So let me call this hardware filter.bmp binary file, no appending, save to be here. Then run your software. Okay, configuration, since we are running the first time, we need to run from here. Launching on hardware. Okay, done. Come back to, okay, so we still have this print DMA initialization success. We need to remove it because you can see in the log file he stored this one, so which will cause problems. So need to remove this print actually. So clear buffer, we need to enable log again. Log hardware filter. Okay, come back, file, send file, stop, and a binary file, open. Okay, we are getting the data back. Okay, my data transfer is completed. I am supposed to get 263.224, but I am getting more than that. That means I still have some print in my code which got logged. So what I can do is in the HXD editor, I can open that receipt file, and I can see at the beginning there is some more data. It is not starting with BM, and he actually shows the ASCII code for each data, so you can see DMA transfer success. That is that extra print. So I was supposed to remove this one also, Okay, so I'm not rerunning my code. What I'm doing is I'm simply deleting everything before 4240s. Okay, to close it, and you can delete it instead of rerunning the entire code. Now if I check, okay, 4043 is 0, so 1 byte is missing. Let me append a 0 and save it and close, and this is the image. So exact same effect you can see. So the hardware filtering is happening, and the output looks exactly same as the software filtering. Okay, so we effectively use the DMA transfer to do it. Now, what's the advantage of using hardware on software? We'll discuss in the next tutorial. So basically, we will compare the performance of doing this operation in software, how much time it takes in software, and how much time it takes in hardware, and compare the performance. Okay, so see you in the next video. Thank you.